Martin, for inviting me. So I'm going to talk about, so the title given to me was Classical and Machine Learning Based Robotics Algorithm. And I will go with that. I will focus on algorithms connected to localization and mapping. I won't really go into the details, but I'm going to try to give you an idea about the problems connected to that. But before doing that, I thought I would try to motivate why I'm working on robotics. So I've been doing that for 22 or 23 years now. I think it's an amazing field to be in because it's combining a lot of different areas. It's not enough to be an expert in control theory. It's not enough to be an expert in computer science. You need to combine many different disciplines and they have to come together. And I also like this physical embodiment part of robotics. We build stuff. And as everyone that has ever tried to build something for real knows, it's never just to put X and Y together. It never really works, at least in the beginning. So there's a lot more to it when you build real systems. And another thing that fascinates me is the autonomy aspect. You press enter on your system and the system has to work. You're not allowed to interact with it really. It has to make decisions on its own. You can't plan for everything beforehand. The system somehow to cope with the environment. I think that's really cool. And I think it has been touched upon previously in this week as well, that this autonomy aspect is really, really challenging. You can have a system that is really, really simple, but as soon as you let go of it and it has to be operating on its own, it has to be incredibly simple for that to work reliably. Just a few video clips here from robots over the years that I worked with. So in the top left corner here is my baby robot, Harry Plotter from 2003. This is a robot that operates at the Stockholm International Fairs, marking the positions of stands at the exhibition so that they know where to put the stand. In the next video you see an example of a big grinding robot that makes floor in, for example, car manufacturing factories very nice and smooth so that it makes it easier to clean. Then we have a robot that makes traffic signs on the roads. So the idea is that instead of having a person being on the road, risking his life, being run over by cars that don't slow down, you can sit safely in the cabin of the truck and point at the screen and say, I'd like you to paint a 70-kilometer sign on the road. These are sort of industrial type applications. I've also spent a lot of time in various research projects. This is an example from an EU project that ran for 4.5 years. The aim was to build a robot, or to look at how we could use the extended experience of a robot to make it improve over time. So the target that was set up was that the robot was supposed to be autonomous for 100 days. That was a bit optimistic. Turns out that it's not so easy, as you can imagine, not only from a software point of view, but also for hardware. You can't really buy a robot today that will actually work for 100 days without any problems. But in the end of the project, we basically had sort of reached the point where hardware and software was at roughly the same level of reliability. So this is a robot that moved around in one of the in an office building in the UK, not really doing much else than just sort of patrolling around and looking for new objects in the environment that it tried to learn models about, and then it used crowdsourcing to help, or to get help by people to say what this thing is so that it could extend its knowledge about the environment. So in terms of improving over time, that helped it improve its understanding of the environment, and then it also used the sort of statistical information about how people move around and which paths are more easily navigable at certain points of time to be able to move from A to B in a faster way. In the middle here we have, so since about 3 years, I have been moving into flying robots, and there we had another level of complication. So there are a lot of drones out there that do cool stuff in the real world, outdoors. But indoors you have the added complication that you don't really have a good positioning system. Things are really close to you. So this is our kitchen, so it's kind of large, but it's still just a few meters to the nearest obstacle, and there's no easy way to get around that. You can't just fly up 50 meters like you can outdoors to avoid every obstacle. So here you have to have a system that's really reliable and safe. And the last video here is from an EU project that ended in the fall of last year. This was 3.5 years looking at ways to increase the automation in sort of search and rescue type robots. The end user here was the German Kerntechnische Hilfsdienst or something. I'm not sure if I got the pronunciation right, but they build robots that are supposed to be used in nuclear accidents. So they have this, currently they have these robots that weigh 1.2 tons that they teleoperate. And the idea was to build a robot that was more lightweight, that was more dexterous, that could actually move in places where the other system wouldn't be able to move. And then there was an operator, two operators actually, that could, when it was needed, take over certain parts of the operation of the robot. And this video, maybe you didn't notice that, but so this is illustrating that the robot has now come to a very critical point. It has moved a few hundred meters into some site where no humans can be. There is a reviewer at the side there, and then the robot is supposed to screw a screw into this wooden piece there. And if you look very closely at the video, you see that the screw bit falls out of the screwdriver. So there, 42 months of work in the EU project, and everything fails because the screw bit falls out. So robustness is I mean, looking at all of these examples, robustness is a very big issue. All right, so what will I talk about? I was supposed to talk about algorithms. I will focus about algorithm for localization and SLAM, or mapping, because robots need to know where they are. In all of the examples, those 6 videos there, the robot had to know where it was to be able to execute its task. And of course, it's not only in robotics where it's important to know your position. This is something that is widely applicable. So in the second part, I will look at how we can use deep learning in the context of SLAM. I will come back to what SLAM means. So I'll try to answer the questions why we do it, where we can do it, and how we can do it. But let's start with sort of the more traditional algorithms and how we actually define the problem of localization, mapping, and SLAM. So starting with positioning. So a localization system is set up there to give us the position. If we are a bit more picky, in most cases we actually want to know the full pose of something, the robot or the drone or our screwdriver or whatever it is we're trying to position. So we want to know the position and the orientation. So when I say pose, I mean position and orientation. When I only say position, I probably mean pose anyway. So this is a really fundamental piece of information that many applications require. Sometimes it's enough to have your position in 2D, sometimes we need it in 3D. If you have a logistic robot that moves around in the warehouse, you are pretty sure that it's going to move on the floor. So we don't really care about where it is in height. It's going to be on the floor. And there are a lot of different examples where this might be interesting. It might be your car, your autonomous car. It has to know where it is in order to know how to move from A to B. It could be a drone. Maybe it's a delivery drone that is supposed to deliver your last purchase from Amazon to your doorstep. Or it might be a person. It's a person. You're at an exhibition and you have some kind of device on you that lets the exhibitors know where you are so that they can present information to you that is very specific to this place you are at. Maybe you're at the museum, which is similar, and you have headphones on you and they tell you something about the piece that you're in front of. You need your position for that. Could be a hospital bed. So the hospital wants to know where is bed so-and-so. And if you are able to position it, you can just go into your computer system and say the bed, someone seemed to have left it in this room over there. Or it could be a package. So that we can track the position of this package throughout the chain so that when you have ordered something, you can actually go and see this is where it is. So a question that you normally get when you talk about positioning is, well, is this really a problem? Isn't there GPS? So is GPS solving all of this? No? Why not?
Not indoor.
Not indoor, yeah. Are there any more problems with GPS? It's not so accurate. How accurate?
Not enough.
Not enough.
Depends.
GPS helps you to know your location, not your destination.
Yeah.
Sometimes you want to see, okay, I want to go there, but I don't know the GPS location there.
Yeah, so in many cases you don't actually care about your absolute position. If I want to go to you, all I care about where you are now, and I can care about my relative position with respect to you. Yeah. So you talked about the accuracy. So normal GPS would be something like 5-10 meters or something, which is not really enough if you want to drive a car on the street, for example. It's not enough for many applications. But it's super if you want to know that you're in Stockholm or you're close to the concert hall and you want to know that if you turn right at the next intersection, you'll come to this or that restaurant and you can have something to eat. But it's not enough if you want to build a robot that moves around in a warehouse to pick up some stock from position X and deliver it at position Y. That the problem there is also, of course, that it's indoor, so GPS wouldn't even work. Yeah, and there are cases, I mean, if you're outdoors, if you do agricultural robotics, you might afford to put an RTK GPS on your system, and then you can get down to centimeter precision. But it's going to be quite expensive and a bit bulky if you're building a small system. Right, so a typical localization algorithm would look something like this. You initialize your position. This could be, so for the robot at the fair that was printing the stands, that's a human telling the robot, you are here. Could be by positioning at a known position, and you always know when you press start, it knows that this is the position. It could be that you get a GPS fix, so you get your rough position and then you get more fine-grained position information after that. And then after that you typically repeat a loop that would look something like, I will predict my position, how I have moved based on some kind of sensor data, and sensor data that is internal to me. Maybe I'm counting my steps. I have a watch. It will count, or I have a watch on the other hand as well. It will count my steps, and by knowing roughly how long my steps are, I can actually estimate how I'm moving. But only how far I'm moving, not in what direction. But if I have some general idea about my direction, I can predict roughly how I'm moving. Then I take information from other types of sensors, something that gives me information about the external environment. I incorporate that and combine it with my dead reckoning information, and I can update my position. Okay, so that's a typical localization algorithm. Now someone is calling me. Okay, so this is an example, one example of how you could do dead reckoning. So if you have a robot with wheels, you might put encoders on the wheels, and you simply count how many degrees the wheels have moved. If I then have a kinematic model for the car, which is straightforward, I can estimate how it's moving. I need to know how the wheels have been moving and how my steering wheel is pointing. And this gives us something typically called odometry. And this is something that will typically be quite accurate over short distances. So if I have encoders on my wheels of a robot, if the floor is really flat, I have really hard, thin tires, you can get this to be really, really accurate. You could drive meters with having very, very small errors, but eventually it will drift. It will drift. And if you drive long enough, you will have unbounded errors. And as you can imagine, if something unexpected happens, maybe there is a wheel slip, like Jana talked about, the robot turns and doesn't really know about it, it will get a really, really large position error. So here's an example environment, and the robot was driving back and forth 2 times in this environment, and just looking at the information from the odometer made the robot think that this is how the environment looks like. So you can see that locally it's kind of accurate. It's only slightly bent, but if you back off and look at the entire trajectory, it's globally quite off. So if you want to have a better positioning system, we have to have something that combines this quite accurate local predictions and makes use of external information as well. All right, so this was dead reckoning using wheel encoders. There are other ways to do it. One way would be to use an IMU. This is what's done in a watch, for example, although it's typically only used to calculate steps in the case of a watch. But you could do more. You could take into account all the information from the accelerometer and the gyro and actually estimate pretty accurate motion of the system, but it will typically only work for a limited period of time unless you're a Saab and have really, really good sensors. Then you can do it quite well over long distances as well. If we have constrained motion, if we know really how the system moves, you know if you're a person taking steps, we're in a corridor and you know that every time the person puts a step down, we can sort of recalibrate things. You can get a model that is relatively accurate also with quite simple sensors. Another way to do it is to use camera images. I take an image, I move a bit, I compare the two images, and now I can calculate my motion. So this is something that is typically referred to as visual odometry. And nowadays you can get really amazing performance using this. We'll show you a video later about this. Another way to do it is to use a laser scanner. Same idea, take a laser scan, you move and you look at the transformation between the laser scans. That will give you information about how you moved. So localization. So the sort of components in the problem here is our robot position, which we're trying to solve for. So this is X in the picture here. We have some landmarks that would be things in the environment that I know the position of. In terms, if it's a GPS system, it would be the positions of the satellites. And then we have measurements, which would be the time it takes for the signal to move from the satellite to me. Or it could be the time or the bearing in an image to a certain landmark. So we assume we know the position of the landmarks. And what we're trying to do is we're trying to estimate the position of the robot. So this is the localization problem. And the type of measurements you have could be almost anything. It could be the magnetic field. If you look at the magnetic field in an indoor environment, you will see that it varies with your position. As long as there's a correlation between your position and what you're measuring, you can make use of that to position yourself. And there are the two most frequently used algorithms for positioning. Algorithms are the particle filter and the Kalman filter. I won't go into them at all, but just for your reference. This is an area that has been researched massively over the past decades. I don't know exactly when it started, I guess thousands of years ago when people tried to go from one place to another overseas, for example. If you look outside the robotics, there is a lot of different other sensors that are often used. So Wi-Fi is quite often used. We have, in most environments today, there are Wi-Fi access points that we could measure the signal strength, for example, to, and then calculate our position based on that. It wouldn't maybe be super accurate, but it's widely available. And in many applications, we don't need super accuracy. We could use Bluetooth in a similar way. We could use ultra-wideband, or we could use 5G that I guess James Gross will tell us more about tomorrow, maybe. All right. So here's a picture from one of the robotics magazines making a commercial for a robot. In this case, it's saying that the robot can see and it can act and it can learn and so on. But at least from a person like me, there is something very wrong with this picture. They're cheating. What are these things? There are small IR reflectors. That means that they probably have a motion capture system rigged up in the room. So they use an external positioning system to find where this thing is. Because it is really hard to solve the localization problem. So they solve it by installing infrastructure. I'm really interested in providing this information on board instead. It doesn't have to be on board, but it should be on board sensors. You could imagine if this system is really small, maybe it doesn't have the power to carry its own computational resources, but at least I'm interested in the algorithms that allows us to calculate where it is based on information from the robot itself. So what if there are no landmarks? We said in this picture here that in order to calculate where this robot is, we need to know the location of the landmark so that when I measure, for example, the distance to the door over there, I can use the known position of the door to update my position. If I know that, then I can solve the localization problem. So what if I measure the distance to the door there? If I'm completely uncertain about my position, what type of, how would my probability distribution of my position look like after I have measured the distance to the door?
Be a circle around.
It would be a circle around the door with the distance or the radius of that circle corresponding to the distance of my measurement. And then I can use more information. I could use information that I know that I'm in this room, and then that would be restricted to a circle that is in this room. I could use information that I'm seeing the window in a certain direction, and then I could say something about my orientation and so on. So in cases where I don't know that there is a door there from the beginning, but I would still like to be able to maybe not find my position in a beforehand defined coordinate system, because that's not possible, but I would like to at least reduce the drift when I'm moving so that I can find my way back, for example. How do I deal with that? Yeah, so we have to build up a map, exactly. And this is what then leads to the so-called SLAM problem, standing for simultaneous localization and mapping. So when I started in '96, I guess people had figured out that this is how you have to solve it, but it wasn't that many years before that people were still trying to solve localization and mapping separately and failing. And looking back, that seems like silly how people could even think that that was possible, but they were doing that. So the idea is that we build a map of the environment. As we go along, we use that map, that partial map, to localize in. We use our updated position that we got based on finding our position in that map to extend the map, and then we go on. So we simultaneously map and localize. So if we go back to that picture we had before, now also the location of the landmarks are unknown, and again the position of the robot is unknown, and we're trying to find both of them at the same time. So a significantly harder problem. So in a way, nothing is known. It's a bit strong maybe to say that nothing is known, because if nothing is known, it's really hard to do anything. So we will typically assume that we have some kind of sensor model, for example. We know that the data we get from our laser scanner is the distance in meters, and we know that the resolution in angle and so on, so we can actually tell where a certain measurement came from in the world. That we will assume, but we will not assume that we know anything about the environment itself. But we will make assumptions. So what assumptions do we typically make when we make maps of the environment, do you think? Flat surface is one example we could, or one assumption we could make, yeah? So people have been doing this for 20, 30 years, and most people still today make one fundamental assumption.
Static?
It's static. So everything that moves is something that is not supposed to happen. This is clearly not the case when you are mapping on the road with cars around you. So you have to do something about it. Yes, most people assume that the world is static. So here's an example of SLAM in action. This is one of our drones moving in one of our labs, or maybe. So you can see how the map is sort of gradually building up as so the drone is flying in a circle like this in the room. And you get this 3D, it's not a complete model, it has a sensor that, a camera-like sensor that has a field of view of something like 60 degrees horizontally and 45-ish vertically, so it doesn't see the ceiling. It doesn't see all of the floor, it saw some of it. So it's a so-called RGBD sensor. Does anyone know what that is? I hear or see some nods. So what's the D?
Depth.
Depth, yeah. So the RGB is a normal color image and the D is depth. So we get both the normal image data and we get the depth data. You can kind of, from this map here, see that the depth data you got over here was quite a bit less accurate than the data that was closer to the robot. So why is that? Sorry? Yeah, it could be a window. In this case, it's not a window here, but that could definitely cause that.
Mirrored, maybe.
It could be mirror, yeah. But there is one difference between the points over here and the points over here. The distance, exactly. So the points over here are much further away, and depending on the technology you use, this could have a big influence on how accurate that distance estimate is. So how does most RGBD cameras work today? Stereo pictures, exactly. And how does the error depend on distance in a stereo camera? Sorry?
1 over distance.
Yeah, so the error increases quadratically with the distance. So the further away, at a certain point, you will get a really drastically large error. And what's the way to reduce the error? You could fly closer, or you could put the cameras further apart. What's the problem with putting the cameras further apart?
Space in the robot.
It would take space, yeah. Yeah, if you put the cameras further apart, it becomes more difficult to find the correspondence between the left and the right image, and this is needed to be able to calculate the distance. So if I want to calculate the distance to the door over there, I somehow have to find the pixels in the right image and the left image that correspond to each other. And the closer I move the cameras, the more similar the images will be, and the easier it will be to find that correspondence. If the baseline is small, that will mean that I will be not as good as estimating distances further away, but that correspondence is going to be easier. If I move the cameras apart, I'm going to be able to estimate the distance better at distances, but it's going to be harder to find the correspondences. And when I come close to object, I might not even see the same thing in the two images. Okay. So when I was a student in the 90s, those two algorithms I mentioned before, the particle filter and the Kalman filter, those were the main algorithms that was also used in order to solve the SLAM problem. But today, most SLAM systems are built in a different way. They're built around optimization. So the idea is you build a graph as the robot is moving. The nodes in that graph corresponds to position where the robot has been, and also map entities. So imagine I want to build a map of the environment here, and I'm using a camera, and that camera is able to detect faces. So I'll take an image, and then in that image I will have a bunch of faces detected. I will move. Now I get another node in my graph corresponding to my new position. I'll take another image, and I will see a new set of faces. Now that graph will consist of my two positions and the estimated position of your heads. And as I get more of those measurements, I will get a larger and larger graph. And every time I get a measurement, I will have an edge in that graph. That edge corresponds to that measurement. So when I solve the SLAM problem in this optimization framework, what I'm trying to do is I'm trying to solve for the position of those robot positions and your faces. So we optimize the graph. We try to minimize the energy in some sense, you could say. So when we change the position of the robot positions or the faces, if that's the landmarks we're using, that costs energy. If you think of the distance that my camera is estimating to your face as being the sort of the nominal distance, and you think of putting a spring into the graph, having your head at the distance corresponding to where my sensors put it is low energy. If I want to change the position of your head or the robot's position, it's going to build up energy in the system. And we're trying to find a solution where that energy is minimized.
But that must all depend on the purpose. I mean, for example, the accuracy, the kind of application.
Yeah, it could be the what would be a reason not to do that?
I'm just thinking that in some applications you would want to spend more energy because you need a more detailed map, for example.
Okay. So energy. So yes. Okay. So we have computational energy and we have energy in the graph. So you could of course spend more or less time optimizing this graph, and it might be that I don't really care because it's not so important. But if I want a very, very good map, I want to spend more computational resources to optimize the graph. But I would claim that you would always want to try to minimize the energy, or minimize the energy in the graph. I mean, to put the variables corresponding to the unknown things here in the best possible position. So here's an example. You only see the positions of the, only see the nodes corresponding to the robot's position, and you see how the map is sort of adjusting a bit as it acquires more information. You see the edges between the different nodes as the robot is moving. And you see as the robot gathers more and more information, it can build a more and more accurate map of the environment. So you saw see when the robot goes down here, you see something happening. You see how the map sort of snaps into a better position. This is something called loop closure. Is that good or a bad thing? It's very good. It's the thing that at least when I implementing the algorithm myself, sort of got a, it was a big rush when you saw that your algorithm actually managed to close the loop and sort of get this global consistency. So if you want to implement an algorithm for mapping, you really want your system to come back to places it's been before. You want to be able to, if you think of it as a graph, you want that graph to be able to connect nodes corresponding to positions that you saw at very different points in time. That allows you to reduce the error in your graph. So you can imagine a car driving around a big loop and then coming back. All the way around that loop, it's only going to be able to use essentially dead reckoning to see how it's moving. But then when it comes back to the same position, if it's able to associate that position to actually being the starting position, it can get a globally consistent map from that. So in practice, if you want to implement this in an actual system, and you want also to control the actions of the robot, to control how it's moving and take mapping into account, you typically want to control it in such a way that it is revisiting places once in a while during the mapping so that it can reduce the uncertainty. The typical setup in a SLAM system today is that you have something called the front end. That would be the system that produces the new nodes. So if I'm moving around here and my system is trying to estimate my position, the front end would spit out nodes as I'm moving. It would spit out nodes corresponding to the measurements, and the front end would try to do its best to reduce the uncertainty as much as possible, but it would not care about the global optimization of the graph. This is something that is offloaded to the so-called back end. So the back end tries to optimize the graph, and this would typically be implemented as two separate processes, or threads at least. And while this runs in real time, because we really want to know our position in real time, we need to know where we are because we want to do control that is based on where we are. The back end can operate a bit slower and sort of do global adjustments to our positions a bit less frequently. So here's an example of a state-of-the-art front end today using visual information. Maybe playing. So now it's playing, right? So you see the camera image, you see the image point that has been extracted from the image, and you see the estimate of the camera motion here. So this is using the camera only, moving through the environment, estimating the position, and you can see, looks cool, right? And from this camera information, it's able to estimate its position really incredibly well. It's not without drift, but the drift is quite low. And you can see that the size of the environment here is quite large. So this would allow us, for example, in a virtual reality or augmented reality application to keep track of our position without using HTC Vive setup or something. It wouldn't be without drift, but you can get quite good position information. So that's the front end. And then we have the back end. So this is the thing that is trying to optimize the network. Most SLAM research today, I would say, operates on the front end. And then many of the work out there are making use of some of the many packages that are available. Here are 3 examples of those. So if you take all of this together and put it into one system that has both the front end and the back end, then one of the examples out there, which has a few years now on its since it was released, but it's still one of the more widely known, and something that if you write the paper you would have to compare to, is OrbSLAM 2. So here's an example from a car. Again, the green dots here in the image corresponds to the feature points that was extracted in the frames. By using those feature points across time, we can calculate the position. You also see the graph being built here. And you will, if you start from the beginning here, you can get an idea about the accuracy of the system. So you will see when the robot, when the car comes back to a place where it has been before, you can see that it actually estimated the intersection there quite accurately. We can also see that they seem to have picked the time of day when there are no other cars moving, just to make sure that the static environment that's a valid assumption. You can see that on the highway as well. I'm not sure when they're driving, but and this you can use indoors and outdoors, of course. So here's another example from an indoor environment. Here you see all the green lines here are the edges between the nodes. Some of those edges come from estimation of motion based on consecutive frames. Some of them also come from these loop closures where you're able to relate frames that are a bit further apart. You can also run this in localization mode, as they call it, where you sort of freeze the map, and now you're only trying to localize with respect to that map. So if you're Google or someone, you would typically go out with your cars, you would gather data from the environment, you would build a map that would allow you later to localize in the environment in a way that is much better than what is possible with GPS. If you want the car to be able to operate in any environment, just go out anywhere in completely unknown terrain, you need somehow for the system to be able to actually detect where the lanes are. It's not enough just to know your position. So if you know your position and you know where the lanes are, you can sort of derive where you are with respect to the lane. But if you want true autonomy, you would actually have to detect the lanes as well. So this was a very, very quick introduction to the area of localization and mapping. There are so much more to say. It's a very well-researched area that has been active since the 90s. There are, I mean, if you look in the literature, people have tried to do SLAM with all sorts of sensors. Depending on, as Martin said, depending on what the task is or the application, some of those sensors would be a good choice, some of them would not, depending on what your budget is, what your requirement for accuracy is. Not to forget what your budget for development is. You always have to think about what the application is. If you're going to build a one-off thing, you may not have hundreds of millions of crowns in development to design the algorithms that will be able to deal with really bad, cheap sensors. Then it might be the only way forward might be for you to use better sensors that require less fancy algorithms. So let me end with by saying what my vision in this area is. So I'm really interested in trying to create maps in an autonomous fashion. So by autonomous, I mean you let go of the robot and it should be able to explore the environment on its own. And I'm looking at applications of surveying or VR. So I want to be able to answer questions. On a basic level, I need to know where I am or where the robot is. And I need to be able to answer how to get from A to B. This is what localization and mapping has been about from the beginning. This is sort of the very fundamental part of it. At the medium level of difficulty would be to try to figure out what the distance is between 2 points. That might seem like a trivial thing, but if you want to be able to do that very accurately in a surveying type application, if a construction company wants to figure out if it's possible to pass through a certain, if their bobcat can pass through this section in a mine or something, you would want your map to be accurate enough to be able to actually say that with high enough certainty. Or I want to be able to measure the distance between the size of a building or something. And might be very important that I get that accurate. So I want to be able to do that. I also would like to be able to say something about what it looks like from a certain position if I look into the map. So that's easy to do if I have actually been there and acquired an image from a certain viewpoint. If I take an image here and someone asks me, what does it look like from exactly this position? It's an easy question to answer. But what happens if I move over here and I want to acquire an image, or I want to deliver an image? It's not as simple. I can take the image I have here and I can warp it to this position, but there will be a bunch of parts in the image where I don't have any data. I have to make guesses basically what it looked like, because those parts of the environment were occluded from my original position. So I would like to be able to make informed and good guesses about what it might look like from a new viewpoint. Or preferably not guesses, but in some cases it will have to be guesses. So if I want to guess what's on the other side of your screen there on your laptop, I can make a very good guess by knowing that this is a Mac 15-inch from so-and-so year. But who knows, maybe there, I mean, now you have your hand there, so, but there could be all sorts of things there. I don't really know. I can't see it. If you get a bit harder questions, I would like to be able to say something about how the map might evolve. In a car driving scenario, that could be something very concrete as being able to tell where the other cars are moving. But I'm thinking here more general than that. If you are, let's say you're mapping again a construction site, then you should be able to accumulate data over a certain amount of time and say something about how the environment is likely to evolve. And then maybe compare that to our building information model and say something about if we're on track and so on. And also, if I want to do virtual reality type applications, I would like to be able to say what happens if I apply force at a certain point in a map. So only using camera information, build a map, and then go into that map and try to do stuff with the environment. What happens if I grab hold of this and lift it? What parts of the map would actually follow when I lift here? That would be really cool. So here is an example of a map where you can see that the map looks really, really good in the beginning there, where you have a viewpoint from where you actually have an image. But as soon as you get a bit out from that position, you start to see the black holes here, which are the missing data. That's not going to look good if you have a really... in most applications, you would want that those missing data segments to be sorted out somehow. And I think with that, I will end. And if you have any questions...
Maybe if you go back to the vision.
Yeah.
So I suppose maybe tomorrow you'll come back to model-based versus or map.
I will. So tomorrow, what I will do is that I will try. So I'm assuming that you all have heard about deep learning, but I'm not going to assume that you know really what it is. So I'm going to give a very short introduction, and then look at how can we make use of that in the SLAM problem. And then think about, I think it would be interesting to think about, there's a lot of talk about how introducing deep learning into things makes it completely impossible to say anything about how it will work, understand what's going on and so on. And I think we could discuss that as well. That would be interesting.
Jana touched a little bit on that, but I guess there are at least two schools. So one school with the symbolic reasoning methodologies.
Yeah.
You have some a priori knowledge. You can reason about the domain.
Yes.
Or you just learn and build that knowledge somehow.
Yes.
So which school do you belong to?
I think I'm somewhere in between. I think you should make use of whatever information is out there. So in most of my previous work, I've tried to make the robot leverage information that is available, but ultimately in a specific environment, it's not really possible to know everything in advance. If I ship a robot to thousands of people, there's no way for me to be able to send them a model of the environment for that specific house it's operating in, or to know how that person, that user is, how it's calling different things. I mean, that's a very basic thing, but that's not going to be so easy to know. So I think we will need to use a combination. I think we need to load it with a lot of prior knowledge, but then it has to also acquire knowledge along the way.
And that knowledge, I mean, the world is evolving.
The world is evolving, so it has to somehow update that. It has to, for this to work, I think you also have to be able to transfer information from one domain to another. So if the robot has learned something in domain A, it should try to make the best possible use of that when it applied to domain B as well. This is maybe not so controversial when we're at the basic research level, but it will be controversial when it has been in your house. And the question is, how much of the things it has learned in your house can we transition when we move the robot to your house? Do you want that? That may be a bit questionable.
Yeah, sure.
David, do you know if people have used SLAM underwater? Does it work
Yes.
with sonar?
Yes.
I mean, there must be particular challenges there.
Yes, it's enormously challenging. So we have actually a large project running for, I think it's 7 years, together with Saab, MMT, company doing underwater surveillance, Stockholm University and Gothenburg, doing exactly that. So one of the things they want to do is they want to go on the ice. And if you go under the ice for hundreds of kilometers and all you have is a sonar, that's quite a big challenge.
Are you using any ranking algorithms for the features, especially in the case the difference between the looping is a very long period of time? If I want to be accurate when, for example, consider a UAV is flying over our area,
Yeah.
and in the first turn it is a spring, but
Yeah.
in the next turn it's not a spring. So maybe there are some lakes, there are not lakes anymore.
Yeah, this is a huge problem.
Are you considering any ranking algorithms for the
So
features?
we haven't worked so much on this specific problem, but there is quite a lot of work on that. I mean, it's a very, very important problem. As you say, the environment might change completely. I mean, it doesn't have to be only winter and summer. It can be from one day to the other.
Yeah.
Could be
Maybe
like the difference between daylight and night. The same environment looks completely different when you have sun up there or sun there, or no sun at all, as is the case in Sweden for a large part of the year. So yeah, that's a huge problem. And when to actually decide that we have closed the loop. Once we make that decision, we're going to create a lot of problems if it actually wasn't a loop there.
Okay. So, thank you, Patrick.